Single replacement. Now let's look at double replacement. First time for any of these reactions that we've been talking about that there will not be any electron transfer. No changing of the oxidation states of any of the things inside. So what does that mean for us? What it means is that you're going to have two ionic compounds. So each of those ionic compounds is going to have its own cation and its own anion. And there's going to be a very simple swapping. You will see this pattern. These are super easy to look at and identify. So look for two ionic compounds on the reactant side. There's going to be two on the right side. The cation-anion combos will be switched and different on the different sides though. And then I have this little note that this is important. Check for the solubility of all these different compounds, because usually something is going on there. Otherwise, it would not really be a reaction. Okay, here's the general form. So as I said before, this would be the cation. This is the anion. Here's the other cation, the other anion. And what's going to happen is there's a switching. So where B was with Y, now B is with X, and the reverse is true over here as well. So pretty simple structure to them. Here is a nice little example for us. We have silver nitrate plus sodium chloride. I'm trying to just indicate to you what compounds I'm using for each ion in here so you can keep better track of it. So this is very soluble. Remember, anything with nitrates are soluble. Sodium chloride, table salt, very soluble. So you put it into solution and you have this mixing of these four different ions. And then two of those ions will find each other and they will bind to each other and they will form a solid and precipitate out. That happens to be the silver and the chloride in this particular situation. So this is why it is a reaction. If this was soluble, if silver chloride was soluble, it's not, but if it were, then you would just have a bunch of ions hanging out inside of a solution. And I would be hesitant to call that any sort of reaction. It would just be some salty water, okay? So it's really important to look at, is something going to be a solid, a gas, a liquid, something like that, other than just plain old aqueous. Here's another example for you. So I've got lead 2 nitrate plus potassium sulfide. Okay, so we've got our lead is currently with the nitrate. Go over to the other side. My lead is no longer with the nitrate. It's now with the sulfide. Again, on all of these things, make sure that you're keeping track of what the charge of the ion is so that you can get the appropriate empirical formulas. In this particular case, lead sulfide is not soluble, so it would be the solid that would come out of solution as a precipitate. Everything else would be left in the solution, and if we assumed that you had equal quantities or the perfect matching of all the different ions, then the only thing that would be left in solution would be our potassium nitrate. There might be small amounts of this, but that's at a different level than what we want to talk about right now. Here's another double replacement reaction that is a specific type. So within the double replacement reaction, we can classify something called a neutralization reaction. I thought I would show that to you. So the neutralization reaction is when you take OHs and you match them up with Hs and you make yourself some water. So I take a base and I take an acid and they neutralize each other and I just get water out of it. So calcium hydroxide, here's the base part. Here's the hydrogen, that's the acid part. For the purposes of this little presentation, I'm just showing it as a nice little hydrogen. Some of you may know that it doesn't stick around. It's just a hydrogen when you're in solution. It goes to an H3O+. So they're kind of equivalent concepts for us right now. But what we're going to do is we're going to do our standard swapping, and then you end up with the neutralization. So the hydroxide and the hydrogen coming together. So it makes H2O. Now, that can be a little confusing to look at as far as the pattern is concerned. And so if you want, look at it like this. Here's your HOH. There's your cation out front, H+, and here's your OH-. So that could help you understand the pattern of the double replacement. All right, that was it for this video as well. So we covered all 5 of these different reactions. Remember, 4 of the 5 were redox reactions where we have the electron transfer. And then our double replacement where there was no electron transfer. So hopefully this was all pretty straightforward stuff. So hopefully that made sense. And if it did, let your computer know.